Hello physics students, welcome to our next unit, which is circular motion. Hopefully most of this will be new to you, so let's get straight into it and into the introduction. Now, circular motion in physics for us is describing when an object goes in a circle, quite clearly. Now, there are some examples where objects go in perfect circles, and we'll be dealing with those sorts of scenarios. But physics can describe situations when it's not a perfect circle, but they're outside of this course. Also, it should be noted that when we're talking about a circle, the motion of the circle is a horizontal circle and not a vertical circle. Again, a vertical circle is slightly different, but it's also outside of our course. So here's the rings of Saturn, which are a very clear example of objects going in a circle. And a perfect circle, and the physics that we're going to learn will describe why they do that. Circular motion is everywhere, of course, and one example would be in roller coasters. Even though this isn't a perfect circle, sections of this would be represented by a circle, and you would hope that the engineers who designed this one and this one, where you hang so your feet are dangling, and this one, all successfully understood the basics of circular motion, so when they designed this. Otherwise it would end up in a bit of disaster. Some people like to go round corners and put smoke off their tyres. It's apparently called drifting, whatever that is, and you should have a good understanding of going around in a circular motion if you're doing that. And even if you don't, the person in here would be doing the sorts of calculations intuitively that you could work out using equations and things. And so they're actually doing physics, even though they might not know it. Now, this is just a bit of a short time-lapse picture of somewhere. And what it's got is the stars, and it's showing that the stars in this picture look like they're rotating around, if this was the southern hemisphere, the south celestial pole, or the northern celestial pole if it was the northern hemisphere, when in fact what's actually happening is, of course, the Earth is rotating. So whilst you're sitting still watching this video, you are still undergoing circular motion because you're moving in a circle as the Earth rotates around its axis. Just another example. So it's everywhere. When you start looking for circular motion, you'll see it everywhere. Now let's describe the physics behind it. A couple of terms first. First one is we call it centripetal force. The force that causes an object to go in a circle is called the centripetal force, and it always acts towards the center of the circle. Remember that. That's always the case. There's other forces that can be associated, but the force that's actually causing the circular motion is acting towards the center of the circle. Now, in this case, there's some weight being swung around. We're sort of looking down on this person. If this string broke for some reason or was released, the object would fly off on a tangent, and this is the path of inertia, and so there's no further centripetal force acting on it. It continues on a circular motion. Now, a few of the equations we're going to use. Basically, the centripetal force is described by the equation mv squared on r, and we'll go into that in a bit more detail. And so to make an object go in a circle motion, we must apply that force, and if you're holding onto it or whatever's holding onto it, you must also have a reaction force, which is equal but opposite. And it says here that when a ball is whirled in a circle, it is accelerating inward. Now that sometimes confuses students. How can this object be accelerating inwards when it's actually always going in a circle and always at the same radius? Well, it is accelerating in a circle. Let's see if this pen works. Yep. Because remember that A equals delta V on T. Okay? And so that can be expanded into delta V equals V minus U on T. So to have an acceleration, we must have a change in velocity. And the change in velocity, if we broke the string, that would be the velocity that it has. And so we could say instantaneously, this is the velocity that this object has. Now, if this object went around to here, it would therefore have a velocity that has the same magnitude but now a different direction, and we would call that v. Now this clearly represents a change in velocity. It's pointing in one direction and now it's pointing in a different direction, and so we must be having an acceleration. And if we're having an acceleration, we can say that F equals ma. The mass is constant, so there must be a force being applied, and we would call this force centripetal force. And we'll delve into the equation shortly. And so that's why we can say that the object is accelerating, even though it's staying at the same radius and going around in a circle. Alright, let's get rid of that writing. Where's my mouse? There it is. Can I get rid of you? Go away, disappear. Oh, it's on the PowerPoint. Come on. That's it. That's a bit better. Right. So some terminology, just whilst we're getting our head around. Frequency is one that you may not have heard of before. It means the frequency of an object or an event is how many times it happens in per second, and the unit of frequency is hertz. So if something goes around twice a second, it has a frequency of 2 hertz. The period is the time it takes for one cycle to occur, and by one cycle we mean the repeat of the motion. So in this case we're talking about a circle, so the period is how long it takes to complete one whole circle. The centripetal acceleration we've just talked about. It's the center directed acceleration of an object moving in a circle. And the centripetal force is of course the force that's causing that object to move in a circular motion. And it can be a pull or a push. We're using the example of a string and a weight on the end of the string, but it could just as easily be if you're going in a car around a corner, the side of the door and your seatbelt and the seat must apply a pushing force for you to actually go around that corner. Think of the back seat of an old bus that's quite long, and if it was slippery and a bus goes around a corner, you would slide along that seat until you hit the side of the bus, and then you would proceed around the corner as the bus pushed you. Hopefully that makes sense. Now centrifugal force, you have probably heard it in the physics world. It doesn't actually exist. It's sort of talking about the reaction force that you feel that is basically supposed to be an outward force, but there's no outward force in circular motion. There's reaction forces. For example, when we're doing something, holding something with our hand and spinning it around, we feel an outward pull, and some people would associate that with centripetal force, but really it's just a reaction force. And there's our circle again. Centripetal force always acting towards the center, and inertia, or the path of inertia, is always a tangent no matter where it is. A couple of examples of circular motion as well. We use it in labs where they use a centrifuge. That's derived from centrifugal force, which doesn't exist, but the name has stuck to these things. These things spin around these vials, which can be blood or samples, and they separate the liquids into different densities. This is an example of a human centrifuge, where there's a little capsule that you sit inside and it's spun around, and you can simulate G-forces on a person, and we're going to show you a video. And this one goes up to 30 G, which would almost kill you, I think. I think you start blacking out at about 7 to 8 Gs. This is an older one, but the reason I'm showing you this picture is I've got a video actually in action, and this was used to train pilots and to get used to the forces that they experience in turning. When jets were first introduced, they had to learn how to turn very sharply because jets could do it, so the pilots had to be able to do it without blacking out. And they also use it for astronauts and testing and lots of other things. So let's just play this little video. It picks up straight away. There's no sound because it's a bit loud. And so there it is spinning around, and it's got up to 5 Gs, and it's going faster and faster, and the faster it goes, the capsule swings around, and so it's always swinging, and you can see that his face is starting to distort as he experiences more and more centrifugal force, and eventually he would actually black out. That's pretty good. And so on our OneNote, there's a couple of videos to watch. There's one on pilot training, which is quite interesting, and there's also one on what's called G-lock, which is when you black out because you experience too many G-forces. So in the next video, we'll actually look at the formulas and some calculations. So that's pretty much enough. Let's call it there, and cheerio.